Hi, and welcome to the presentation of electrolysis and anhydrous electrorecombustion, that is a free thermal energy production by alternating current. A Canadian patent application by myself, Paul Welk. Feel free to contact me at this email address if you would like. The Canadian Patent Office will lay this patent application open for public scrutiny on October 2016. However, before then, let me introduce to you the essence of this process. It's an electrochemical process. We start out with potassium hydroxide, which is exposed to electricity, alternating current, and we end up again with potassium hydroxide and an energy which is higher than the energy that we started out with. The energy is derived from the secondary energy source, which is the chemical interaction of atomic electromagnetic energies of elements. By a series of exothermal chemical reactions, we are producing excessive amounts of energy which exceeds the input. So we are dealing with two types of energy. We're dealing with electric energy, which is measured in volt-amp minutes. Here is a formula to do that. To compare volt-amp minutes with calories, we must use a conversion factor. The publicly acknowledged conversion factor is listed there for you. It is 14.34. Once you have converted volt-amps to calories, then you can compare input with output, and that is the objective of this particular test. We will take various readings, new readings, which will be almost identical to what are before you, and then you can verify by doing the math yourself whether in fact this percentage rating of the efficiency is true. Enough said. Let us have some illustrations. Here we have an electrolytic cell made out of stainless steel. It has two electrodes with provisions for electric current being provided. This device has worked very well for me, but there's a problem. You cannot see what is going on, so that you can see as if it were inside this process, I have set up for you a different process where we have a car battery for our initial illustration, and then we have an electrolytic cell of potassium hydroxide. We have two electrodes. We have a power supply, and we will go right into the first phase of the illustration. The first phase of the illustration completes the DC cycle of the 12-volt car battery, and you can see what most likely you expect to see: hydrogen and oxygen being released, which escapes into the atmosphere. Profuse amounts of hydrogen and oxygen. Okay. This will help you understand how the process works later on. We will not spend any more time on this. This is only a preliminary illustration. The real illustration is coming up right now, and I'm setting down the camera so that I can change the voltage supply from DC to AC, turn my gauges on, and show you what we have. We have the electrolyte already mentioned. We have a means to measure the temperature in Celsius or Fahrenheit. The temperature right now is just between 19 and 20 degrees. This reading is very critical because on it the success of this process depends. So before you have the voltmeter, it is set for AC, as you can see, the amp meter, and I was trying to insert the electrode exactly at the half-minute mark. I failed, so we'll go for another 30 seconds, and I get the electrode ready, and I will insert the electrode when the second mark is 60, 58, 60. There we go. The electrode is inserted at 18 minutes after 2 o'clock. The reading is 8.5 volts, 13.4 amperes. So this gives us the figures necessary for the calculation of the energy input. Volt, amps, minutes, multiplied times volts times amps times minutes gives us the volt amp minutes, which by a conversion factor of multiplying that number of volt amps times 14.34 gives us the calories. The calories are determined by the volume of the electrolyte. We have exactly a pre-measured amount of 1000 cubic centimeters. We took the reading just a little bit below 20 degrees Celsius, and we will take a final reading near 50 and then calculate the input, calculate the output, and compare the two. Before we looked at the electrolyte in the DC circuit. Now let us look at the electrolyte in the AC circuit. Again, there is a reaction going on, but it appears that the reaction at the electrodes is pretty well balanced. There is not one that produces twice as much as it did before, when it produced 2 for each single oxygen, 2 hydrogen for 1 oxygen. Let's take another look at it from the side, and I will leave it in this position for a few minutes and try to give a verbal illustration, explanation for what is going on. So bear with me for a few moments, if you will. The difference between DC and AC is really a theoretical thing, because electricity doesn't care in which direction the current flows. Electricity is electricity, and the only difference is that the side effects from the electricity. So when we had a positively charged electrode, the positively charged electrode released the oxygen. When we had a negatively charged electrode, the negatively charged electrode produced the hydrogen. But in an AC circuit, the electrode is positively charged and negatively charged at 60 Hertz. 60 Hertz means 60 cycles per second. So 60 times per second, each electrode is positively charged and negatively charged. So for 1/120th of a second, the electrode is positively charged, and then again for 1/120th of a second, the electrode is negatively charged. So in effect, every 1/120th of a second, the proportionate amount of the water ratio H2O, hydrogen and oxygen, is released into the electrolyte. So hydrogen and oxygen are simultaneously released at each electrode. But why do we not see the same bubbles rising as we saw before? Because when the voltage changes from the positive cycle to the negative cycle, the voltage is at a momentary standstill. When that voltage is reinitiated and the flow of electrons is reinitiated, that flow of electron acts as if it were a spark plug. And you add a spark to the existence of atomic hydrogen and atomic oxygen, they recombine. They recombine, and what we have is electro-initiated recombustion of hydrogen and oxygen. What we have rising here is neither hydrogen nor oxygen, but the consequence of their ignition. What we have rising here is steam. Steam is rising. We have the creation of energy, steam. Now, lest you think I'm just barking up the tree here, look at these facts. During my brief presentation, the temperature has risen from 20 degrees to 47, 48 degrees, and I have to step over here to our meters and turn off the process. I will wait until the conclusion of the half-minute mark at 24 minutes after 2 and 30 seconds after 2. I will extract the electrolyte and discontinue the process. Before I do that, please take note of the readings, because they're changed now. Okay, the process is complete. The only thing that is required now is the reading of the temperature. The temperature is above 50 degrees. Okay, we can look at that later again when we replay the camera and calculate our percentages of power input and power output. On the basis of these formulas, we will now calculate the efficiency, and I predict that it will be much the same, possibly even higher. Let me read now the bottom part of this sentence here. Perpetual free electric energy is available if thermal energy can be reconverted to electric energy at a ratio of at an efficiency of plus 40%. What does that mean? It means that we have an electrolytic cell which puts out steam, and if there is a generator, an engine, a turbine, whatever the case may be, which reconverts the steam, the excessive amount of energy which was produced, into kinetic energy at a ratio better than 40%, then we may drive a turbine and create the electricity which created the energy in the first place, condense the steam, recycle the steam, and have an eco-friendly, ever-producing, never-ending process and supply of energy. Energy which could be applied in many different ways. It could be applied by heating office buildings. It could be applied by driving engines. It could be applied by providing power for energy grids. Our time is up. Thank you very much, and please inquire about it.